Okay, so this video is intended to uh, just go over a topic which is very important in control systems, and that topic is partial fraction expansion. All right, specifically, I want to remind you, or tell you perhaps for the first time, that we have a transfer function h of s, and that's equal to y of s over r of s, and it's some polynomial in s on the top and some polynomial in s on the bottom. And on the bottom, we could split these things up to be the individual roots. And it turns out that h of s, which we have right there, is also equal to a over s minus the first root of the denominator plus b over s minus the second root, all the way up to however many roots there are. We'll say for the sake of this video that there are n roots in the denominator. So as long as we have distinct roots, what we can do is find a by taking the multiplication of what's below a times h of s and evaluating when s is equal to p1. Alright, what will happen is that s minus p1 will cancel from the original h of s, and then we're going to evaluate it at the residue or the critical point. Same thing for each of these as long as all of the roots are distinct and non-repeated. On the other hand, if I have repeated roots, for example, if I have s minus p1 and s minus p1 squared, or in particular, let's write out, this is the original h of s would be something, which I'll just denote as asterisk, over s minus p1 squared. And when I take the partial fraction expansion, what I need to notice is that I have two roots here, and so I need to have two components here. And so I do that by taking both the square and the single. All right, and then b would be found the same way as normal. We would take s minus p1 squared times h of s, evaluated when s is equal to p1. And to find a, what we would do is we would take the derivative of that same expression and evaluate at that critical point. All right, so that's just a very quick reminder of that.